Welcome, learners. My name is Mr. Lola once again, your teacher on this platform, which is called Black Slides Online Secondary School. We are found here on YouTube, where we teach all the sciences being offered at Msce. All right, we cover topics from Form 3 and the Form 4 syllabus. If you are in Form 3 or Form 4, this is your place to be. If you are watching us on YouTube for the first time, consider subscribing to the channel so that every time we upload a new video lesson, you will become the first one to know. So recommend our videos to your friends, wherever they may be, so that they too can learn and prepare for their Msce examinations. I'm wishing you all the best as you prepare for the 2026 Msce exams. Make the best use of our channel, Black Slides Online Secondary School. Inform your friends. If you are a parent, consider buying your child a phone or allowing them to have access to a phone or laptop, and stuff them with enough internet data, so that they can learn while at home. Welcome one more time. If you are a teacher, I also invite you to support the course, to support the channel in any way you can, whether by contributing lessons or in any form of support. You are welcome. My name is once again Mr. Lola, your teacher on this platform. At Black Slides, we are happy to have a platform specifically designated for the teaching of Msce sciences. So other than the YouTube channel, we also have a platform where students enroll into at a small fee of 18,500 kwacha per term. Welcome. In case that's what you want, don't hesitate to reach out to me on the numbers shown here, or you can send us an email expressing your interest. We are going to be excited to be with you, to guide you, to teach you, to mentor you until you are prepared for your Msce exams. We meet in this lesson now for a topic called digital electronics, and we are going to be looking at the subtopic logic gates. All right, so we've come from far with this topic. So far, we've covered 3, if not 4 lessons on the topic digital electronics. So this happens to be a subtopic of the topic digital electronics. Welcome one more time. All right, so let's be together up to the end. It is hoped that by the end of the lesson, you should be able to define logic gates and state their role in digital electronics, the role of logic gates in digital electronics. So we shall give a definition. Definition of logic gates. Define the concept or the term logic gates. Identify and describe basic logic gates. At this level, we are asked to discuss and or and a not get. We should be able to interpret truth tables for each get. We shall see what truth tables are. Apply logic gate functions to simple digital circuits. So these are the areas that we are going to dwell on. Let me urge you to pay attention, take notes where I feel it's necessary. If you are left behind, maybe some point is not made clear to you, don't hesitate to drop a comment in the comment section if you're watching us on the YouTube channel. But if you are learning in the main classroom, simply comment to the lesson. There is a section for commenting below each lesson. We'll be glad to address any concerns that you might have. Once again, welcome. All right, so let's define logic gates. So what are logic gates? In 1-mark question, define the term logic gate. We define logic gates as electronic circuits that process binary inputs. Logic gates are electronic circuits. So logic gates are circuits, electronic circuits, which process binary numbers. Binary numbers are zeros and ones, or binary inputs. So logic gates are the foundation of digital systems, of calculators, mobile phones, and computers. Like right now, if you are watching this video lesson on a phone, mobile phone, be it a laptop or tablet or anything that is internet enabled, it means you are using the application of logic gates. So laptops, calculators, mobile phones, iPhones, tablets, iPads, laptops, desktop computers, TVs, decoders, name it. All these make use of digital electronics. So each gate performs a specific logical function, which is called decision making, as we shall see. Welcome once again. Please kindly share this video to your friends so that they can also join us on YouTube by subscribing to this channel. We want to prepare everyone. We don't want to leave anyone out. Don't be out of class. Be inside class. Don't bunk classes. Stop bunking classes. Come back to class. Be in class. Be here. This is your school. This is your place to be all the time. As teachers at the Black Slides, we are so excited with what we are doing to support everyone intending to excel academically. So welcome one more time. Instead of wasting time on social media, on WhatsApp, and the like, Facebook, make the best use of your phone by being here. We want you to be here. We want you to learn. We don't want you to be anywhere else but to be here and learn. So welcome once again. All right, just to bring you into perspective, welcome once again. Let's look at this comparison or an analogy, just to bring you into perspective of what we are doing, we are discussing. Let's suppose we have a situation whereby the weather is certainly showing that it's going to rain. And you also have an umbrella. That's well done. You are planning to go out. Your planning to go out depends on two conditions. Condition number one, if it rains and that you have an umbrella, then you're going to go out. Let's suppose that it's going to rain, it rains, and you don't have an umbrella. You will not go out because you get wet. All right? Let's suppose that it doesn't rain, but you still have an umbrella. Why should you carry an umbrella when it's not raining? No need, eh? Of course, there are some people we see around town carrying an umbrella here and there, even when it's not raining. Well, that's okay. It's better be safe than to be sorry in case it rains. But here, let's look at these two conditions. It is going to rain. All right. If it rains, then you must have an umbrella. Umbrella spelling. This is going to be equal to going out. So your going out depends on these two conditions. Rain plus umbrella, go out. So this is similar to an AND gate. Both it rains, and I have an umbrella is equal to going out. I hope we are together there. If we are, please comment in the section below. In case I've left you behind, don't hesitate to say that you have left us behind, sir. Please come again. We are going to come again. Welcome once again. My name is Mr. Pochilola, your teacher. We are excited to be here to teach, to help you, to prepare you for your future. Your future lies here. Let's work together and achieve the best we can. All right? God will help us do it. We'll make it. God is good all the time. All right, so we have three types of gates that we are going to talk about. We are going to discuss AND, OR, and NOT gates. What are these things, in case you're wondering? An AND gate is a switch in which the output is equal to 1 if and only if both inputs are equal to 1. All right, imagine you have a circuit in which there's a bulb, and that bulb is connected to the source of power, the battery, quite all right, yes. And it's also connected to two switches in series. For the bulb to light, both switches must be closed. Both switch A and D. The name AND is coming from the fact that both switch 1 and switch 2 must be closed for the bulb to be on or to give light. That's the action of an AND gate. The symbol of an AND gate, which I'll see in the next slide, the shape, it has a D shape. An OR gate, on the other hand, is one in which the output is 1 or on if at least one input is 1 or on. This happens in a situation where you have a bulb connected to a source of power such as a battery, quite all right, and you have two switches that are parallel to each other. So for the bulb to light, either of the two switches must be open, must be closed. It's either switch 1 or switch 2 must be closed in order for the bulb to be on. Remember, 1 means on, eh? Yeah. When you say 1, it means on. 0 means off. Yeah. So we are saying in an OR gate, either switch 1 or switch 2 must be closed for the bulb to light. But if one of them is closed while the other is open, it will not give light. Even if both switches are closed, the bulb will still not give light because of short circuiting. I'm going to illustrate this later on. All right, so the symbol for an OR gate is a curved input. I'll show you the symbol shortly. Thirdly, we have a NOT gate. NOT gate is where an output is the opposite of the input. This kind of switch, I'm sure you have experienced this in your house. When you think that you're turning on the bulb, the bulb turns off. When you think when you are turning off the bulb, then that's when it lights. Okay, that's an example of a NOT gate. All right. So when you turn it on, you are actually turning it off. When you're turning it off, you are actually turning it on. It does the opposite. We have people like that who behave like NOT gates. When they say yes, they're actually saying no. When they are saying no, they're actually saying yes. All right? Okay. That's just by the way. Once again, welcome to the channel. My name is Mr. Pochilola, your passionate teacher. Teacher by choice, not by accident. All right. Welcome once again. So, the symbols of the gates we just discussed are shown here. An AND gate is like a D, you see, but with a long protrusion this end. This is called AND gate. An AND gate has two inputs. All right, has two inputs. You can call this input A and input B, and the one output. Let's call it C. So we are saying the condition for which the C must be a 1 is that both A and B must be 1. Then C is going to be 1. Imagine the C is a bulb, and the A and B are switches which are in series. So we are saying switch A and switch B must be closed for the bulb C to light. But if any one of them is open, because current does not pass through a gap, and the other one is open, closed, still you will not have, the bulb will not light. If both of them are closed, they are off, this bulb will not light. We shall see this when we are looking at truth tables. All right, how each works. So as an exam tip, make sure you know the symbol and its action, the action of the switch, the AND gate. An OR gate, on the other hand, is curved inwards like this. It's curved input, and it has one output. So there's input A and input B to give us output C. Imagine C is a bulb again, once again. A and B are switches, where you can either open or close. The bulb will give light if and only if either A is 1 or, either A or B is equal to 1. So it gives a positive output of 1 when A is 1 and B is 0, or when B is 1 and A is 0. But when both A and 1 are 1, C will not give us any output. It will give us a 0. And then we have this NOT gate. When the input, so this is input A and output B. A NOT gate has only one input and one output, but it does the opposite. When the input is 1, the output is 0, and when the input is 0, the output is a 1. I hope we are together there. Once again, welcome to the channel. This is your home to be. This is where you learn the sciences, namely physics, biology, and chemistry. You can produce the whole certificate with us. Consider subscribing to the channel. If that's what you want, you can go ahead and subscribe. Invite your friends that it is possible to learn here entirely for free. But in case you need one-on-one help and support, don't hesitate to join us in our main classroom at a small fee of 18,500 kwacha per term. Places are still filling up. You are most welcome. Once again, my name is Mr. Pochilola. All right. So let's now look at what we call truth tables. Truth tables show all possible input combinations and their outputs. That's what truth tables do. They are helpful for analyzing digital circuits. All right, as you are going to see, truth tables show all possible input combinations and their outputs. They are essential for analyzing digital circuits. Let's look at an AND gate. Let's suppose that we have a circuit in which we have a bulb. Let's say this is a bulb which is connected to a source of power such as a cell. Let's suppose we have a cell here to power up the bulb, and then we have two switches. Right, so we have two switches. We have switch 1. Okay, instead of using a 1 or what, let's just call this switch. Alright, let's call this switch A and this B. Notice that these two switches are in series with each other, meaning they are in the same path of the circuit. So let's suppose that switch A is open, which is 0 here, as well as switch B is also open, which is 0 here. The bulb will not give light. The bulb will not give light. Let's call the bulb Q. The bulb will not give us light. It will be 0. So here it means switch A is open, that's why there's a 0 there, and the switch B is also open. Current will not flow through the gap. Therefore, the output, which is the bulb, will not give light, 0. Suppose we leave switch A open, 0, and the switch B closed, 1, the bulb will still not give light. Why? Because current does not flow through a gap. This is open switch. Another possibility is to have switch A closed, but leave switch B open, like it is in here. There will be no light there. The only situation where the bulb is going to give light, 1, is when both A and B are closed. A is 1, B is 1. Both switches are closed. Therefore, we are going to have a bulb which is producing light. So this is closed, then we have light on the bulb. That's what it means. That's the action of an AND gate. So we are saying both A and, the AND is coming because you say both A and B must be closed for us to have a high output, a 1. Great. Let's look at an OR gate. An OR gate is a situation whereby you have a bulb, quite alright, and then you have a source of power. Let's say we have a cell here. Alright. And then we have two switches. We have switch A, call this switch A, and another switch which is connected in parallel to A. Call this switch B. Alright, so what the OR gate does is that for us to have a positive input output, a 1 here, one switch must be closed. Let's say we close A. Okay, let's start from a situation where both switches are open. If switch A is open, switch B is also open. Remember, current cannot pass through a gap. Therefore, the bulb will not give light. If switch A is open, 0, and we close B, current is going to flow through switch B, allowing the bulb to produce light. So when A is open and B closed, current will still find its way to pass through this path, and light the lamp there. If A is closed and B is open, current will flow through switch A and light the bulb there. But too bad, when both two switches are closed, we close A, close B, the bulb will not give light. Why? If you close switch A and switch B, what's going to happen is a short circuit. There will be a short circuit whereby current prefers to flow through the shortest route. So the shortest route will be created, and that's where the direction, the path the current is going to choose. So the two switches must not close at the same time. One must open, the other one must close. Then current will flow through to give us the light there. In special occasions, the bulb is going to light. It depends on the material that makes up the switches. Let's say close both switches, then current indeed is going to flow through. But in the event that there's a short circuit, then you will not have a light in the bulb. This must be 0 also. So it's either A or B that needs to be open, to be closed, not both of them closed, but only one of the two should be closed. Then we are going to have a positive output. A NOT gate is when one input is high. Let's suppose this is high. This is going to be low. When the input is 0, the output is going to be a 1. When the input is a 1, the output is going to be a 0. It does the opposite. All right, lastly, let us look at the application of the logic gate functions to simple digital circuits. Gates can be combined to form more complex circuits. For example, you can combine gates, a NOT gate and an AND to produce a NAND, or a NOT gate and an OR gate to produce a NOR gate. These circuits are used in calculators, traffic lights, and mobile phones. So mobile phones, traffic lights, calculators work on the basis of combination of a number of gates. For example, a circuit with two switches A and B connected to an AND gate will produce something else. A light bulb turns on only if both switches are on. All right, that's an AND gate. Yeah, so here we have a situation where we have combined 3 gates. We have an AND. This is an AND gate. An AND gate, a NOT, to form what is called, or to produce an OR, or to produce, we have an AND, NOT, and the OR gate combined. Yeah. So let's suppose that, let's look at it, the analysis of it. So our inputs are A, B, X, and Y. Let's say A is 0. When A is 0, B is 0. This is AND gate, remember. X is going to be 0. When B is 0, that 0 will be converted into a Y, which will give us a 1. So, in order to produce Q, We have a 0 here and a 1. Remember what an OR gate does? So a 0 and a 1 will produce a 1 this end. Once again, when A is 0, B is 0, X is going to be 0, this one here. When B is 0, Y is going to be a 1. So we have a 0 here and a 1 here. 0, 0 and 1 produces a positive output, 1. So Q is going to be 1 when X is 1. When X is 0 and Y is 1. Let's look at the second case. When A is 0 and B is 1, an AND gate will give an output of 0, so there will be a 0 here. When B is 1, the NOT gate will turn it into a 0. So we have a 0 and a 0, therefore Q will be a 0. When A is 1 and B is 0, X will be 0. When B is 0, Y will be 1. A 1 and a 0 and a 1 will produce a 1 here. When A is 1, B is 1, X will be 1 over here. When B is 1, Y will be 0. Then a 1 and a 0 will produce a 1. So we have combined these three types of gates together to produce this possible outcome. I hope we've been together. In case there are questions you need to ask, don't hesitate to reach out to me on the numbers I shared earlier on. Once again, my name is Mr. Pochilola. I'd like to leave you now. Bye-bye for now. If you are in our main learning platform, don't hesitate. Go ahead and do the assigned work. There are questions there in PDF format. Don't hesitate to download the questions and forward the answers to me. For now, bye-bye. We meet again in the next lesson.